Hello and welcome to this lecture on fundamentals of electric drives. In the last lecture, we have just started about the Swiss reluctance motor. Swiss reluctance motor is a lightweight motor which finds application primarily in space applications because of high torque to weight ratio and low rotor inertia. However, as the name implies, this motor has to be switched at regular intervals with a position sensor to optimize the torque production. Let us discuss the operating principle of Swiss reluctance motor. So, we have in the last lecture we have discussed this, that the energy stored in an inductor is given by half Li square. Now, if this energy is stored in the magnetic field. So, this energy is stored in the magnetic field. So, if we differentiate this energy with respect to theta is the position with constant current, we find that this equal to half Li square dl by d theta. So, if the inductance is a function of theta, there is a torque production. It means by relative motion of the stator and the rotor, if the inductance changes, then there is a definite torque production which comes out of the motor. So, T is equal to half I square dl by d theta. So, if you have to optimize the torque, what we have to do here is that we have to optimize this expression. Now, how do I optimize this? We optimize this by switching the current I at the positive dl by d theta. So, that the torque is always positive, because the current is I square. So, it does not matter whether the current is positive or negative, the torque is always positive. However, the torque depends on dl by d theta, which could be positive or which could be negative. So, current is switched during dl by d theta, which is greater than 0. So, in that case the torque is positive, and if you want to make torque negative, current has to be switched for positive torque, and if you want to make the torque negative, we have to switch the current during dl by d theta less than 0. Now, if you see the structure of this motor, the motor has a stator and a rotor. The stator has got salient poles. We can see that we have got 8 poles here, 1, 2, 3, 4, 5, 6, 7 and 8. The rotor and the stator carries winding. So, each pole has got the windings. So, each pole is considered to be an inductance, and the rotor has got 6 poles. We can in fact name them as 1, 2, 3, 4, 5 and 6, and the rotor does not carry any winding, it is just plain slotted rotor. So, when the rotor rotates, there is inductance variation. So, it means we have dl by d theta, theta is the rotor angle. So, as the rotor rotates, we have the inductance variation of each phase, and that is why we have a torque production here. And what we have to do in this case is that we have to switch the current for dl by d theta positive or greater than 0 to have positive torque. This is the principle of Swiss reluctance motor. Since the current is switched, we call this to be a Swiss reluctance motor. Now, we will take an example of a 6 pole rotor and 8 pole stator Swiss reluctance motor. This is also known as SRM. In brief, we can also call this as SRM. Now, in this case we have 8 pole stator, this is what we are trying to discuss, and we have 6 pole rotor, and the stator carries windings, rotor does not have any winding. So, we have for the specification, the specifications are as follows. So, we will be discussing about construction of a typical Swiss reluctance motor SRM. So, what are the construction parameters? We have 8 stator poles, or we can call this as stator teeth, and we have 6 rotor poles, or rotor teeth, and we also have a ratio which is called the tooth to tooth pitch. This given here is that tooth is to tooth pitch which is same as pole arc to pole pitch is equal to 0.4. What does it mean? We have the pole, tooth and slot like this. The ratio between this is the pole arc, and this is the pole pitch. So, the pole arc to pole pitch is equal to 0.4. It means 40% of the pole pitch is occupied by pole arc. So, this is true for the stator as well as for the rotor. Now, since we have already defined that we have got 8 stator poles and 6 rotor pole, we would like to find out what is the stator pole pitch and rotor pole pitch. So, we can find out that stator pole pitch, because we have got 360 degree is the total circle, by 8 we have got 8 stator poles. So, per pole we have got 45 degree. So, pole pitch is 45 degree. In terms of the angle, this is 45 degree. And what about the rotor pole pitch? Rotor pole pitch is equal to 360 divided by, we have got 6 rotor poles here. So, divide by 6. So, we get here 60 degree. And we have also defined that pole arc by pole pitch is 0.4. So, we can decide on stator pole arc is equal to pole pitch is 45 degree into 0.4 is equal to 18 degrees. And stator slot arc is equal to 45 degree minus 18 degrees is equal to 27 degrees. So, what we mean by this, if we have the stator and the rotor, stator pole arc is like this. This is the stator. So, this angle is 18 degrees. This is the pole arc, and this is the slot arc, and the rotor is here. This is the stator side. We have the windings here, winding from the stator, and the rotor is somewhere here below this. So, we have the rotor slot is also of this sort, we have got slot structure. This is the stator and we have the rotor here, and stator slot arc is 45 minus 18 degree. So, this is 27 degrees. Similarly, the rotor pole arc is equal to rotor pole pitch is 60 degree. So, that into 0.4 is the rotor pole arc. So, 60 degree into 0.4, that is equal to 24 degrees, and rotor slot arc is equal to 60 degrees minus 24 degrees is equal to 36 degrees. So, if we consider the rotor pole arc is this is the rotor pole arc, and this is the rotor slot arc. So, this angle is 24 degrees and this angle is 36 degrees. So, we are expressing all the parameters, all the distances in terms of angle. Now, we have to see how does the inductance vary when the rotor moves under the stator. When the rotor moves under the stator, the rotor pole comes under the stator pole. So, there is a gradual increase of inductance, and when this moves away, the inductance decreases. We will try to understand this by drawing a few diagrams. So, here is our stator. The stator has got 18 degree as the pole, and this is the slot here. So, this is 18 degrees pole arc and the slot arc here is 27 degrees. And what about, and again this repeats here because these are periodic patterns. So, what we have tried to do here is that we have caught a stator and we have tried to open the stator. We have developed the stator. So, we are able to see the angle as the linear distances. So, this is the stator that we have already mentioned here, and this is the pole arc and this is the slot arc. And below this we have the rotor. The rotor pole is 24 degrees and the rotor slot is 36 degrees. This is the rotor and this repeats. And the stator carries windings. So, we have windings on the stator. So, this is the stator pole and this carries windings. And the rotor slot arc here is 36 degrees. This is the pole arc and this is the slot arc. Now, the rotor moves in this direction. This is the movement of the rotor. So, it moves along this direction. So, this is, it makes the angle theta as it rotates. So, the rotor moves below the stator. So, when the rotor comes under the stator, there is a gradual increase of inductance. So, the inductance increases gradually, linearly in fact with theta. So, we can define the inductance as the permeance in this case is mu naught L axial into r theta by L g. L g is the air gap. So, this is the rotor pattern. This is basically a part of a cylinder. So, the rotor is moving, and when the rotor is moving, we have to find out what is the area which is overlapping. So, there is overlap. So, the rotor comes under the stator. So, when the rotor comes under the stator, the air gap length here is, this is the air gap length, and this length is L g, this length is L g. What is L axial? The L axial is axial length, which is this length. This is the axial length of the motor or axial length of the rotor here, and the angle is theta. Here it is shown in the linear fashion, the angle is theta, which is the overlap angle here, and area which is this is given as, and the radius of the rotor is r. So, this arc, the arc which is overlapping, and this arc is r into theta, and L axial is the axial length. So, this area which is shown here is L axial into r theta. So, this is basically the permeance. Permeance is mu square, mu naught is the permeability of the air, and area divided by the air gap length. So, we assume here, assuming iron to be infinitely permeable, iron to be infinitely permeable. So, this is the permeance of the air gap. So, what about the inductance? Inductance is nothing but N square into permeance. So, that is equal to N square mu naught L axial r theta by L g. So, what we find here is that as the rotor comes under the stator, there is the gradual increase of the inductance, and the inductance is given by N square mu naught L axial r theta plus L g plus some initial value of inductance which can be L minimum, which can be L minimum. So, this is some minimum value of inductance here. So, this is L minimum plus N square p. So, the inductance variation will look like this. So, if you see that the inductance is a function of theta, and L minimum is the minimum inductance in which the rotor slot arc is facing the stator pole arc, and then as the rotor pole arc comes under the stator pole arc, there is the gradual increase of the inductance, and the inductance is a function of theta here. So, if we try to see the variation of inductance, the variation of inductance will look like this. So, we will start from, let us say, this position, and as the rotor rotates, as it comes under the stator for 18 degree, there is an overlap. So, this basically increases for 18 degrees. So, this is 9 degrees, this is 18 degrees, and then the overlap continues till 24 degrees. So, 24 degrees. So, it means plus 6 degrees. So, this is continues for 24 degrees. So, this is 18 degrees, this is 24 degrees, and then the rotor goes away from the stator. So, the rotor slot will be coming here, the slot arc. So, in that case the slot is actually 36 degrees, this is 36 degrees. So, for further 18 degrees, basically it will go on, this will decrease, and it will gradually go on decreasing for the further 18 degrees. So, 24 plus 18 will be 42 degrees, and then this will again the same thing will repeat here, and this basically will remain in the low position till 18 degrees. So, which is 60 degree here, and then this will repeat. So, the inductance variation is somewhat like this. We have some L minimum here, and we have the inductance is a function of theta. This varies like a trapezoidal signal, and in the x axis we have theta. We are plotting the inductance as a function of theta. So, what is important to us here is that the inductance should vary with the rotor position, and here we are observing that as the rotor moves below the stator, there is a overlap. So, the rotor and the stator are overlapping, we have maximum inductance, and the rotor goes away from the stator, the inductance again decreases to a minimum value. So, this continues because we have repetitive slots and poles, and hence this is a repetitive waveform. Now, since the rotor the stator inductance is a position of theta, we have got dl by d theta. So, we will plot here dl by d theta against theta. So, we will plot here, this is the inductance here. What is the derivative of inductance with respect to theta? This is a 0 in this case. So, till 18 degrees we have dl by d theta is constant, dl by d theta is constant because this is rising, and from 18 to 24 degrees the inductance is constant. So, dl by d theta is 0, and for 24 to 42 the inductance is decreasing. So, dl by d theta is negative. So, this is the variation of dl by d theta, and from 42 to 60 degree up to this point the inductance is constant. So, which means dl by d theta is 0, and this will repeat further again from 60 to 78 degrees, and so on the inductance gradually increases. So, dl by d theta is positive but constant. So, this is the variation of this is the slope, this is dl by d theta, the derivative of L with respect to theta. Now, our objective is that since dl by d theta is becoming positive and negative, we have to switch the current during positive dl by d theta. So, the current predominantly should exist here. If we have a current waveform or a current signal, the current should try to be along this position. This should be the current. So, the current should be only present during positive dl by d theta, not when dl by d theta is negative. So, if we would like to plot the current. Now, let us see what happens when we try to do that. Now, we implement this by having a simple inverter, half bridge inverter. Let us say that we have the half bridge structure like this. So, we have the stator winding like this, and we have a power transistor which is switching the voltage, and so the current, and we have a diode here. So, let us say we have a simple structure in this case, we have a half bridge structure. So, we apply VDC and we apply VDC here, and this is the stator winding. So, when the transistor T is on, what happens is that if we say that we have got the terminal here is A and B. So, if we say this is our voltage V in this case. So, if T is switched on, V is positive, that is VDC. So, the current flows like this. This is what we have here is this is A and this is B. and this is our V. So, V is applied across the winding if T is on, V is positive. So, we can say that if T is on, V is equal to VDC. If T is off and D is on, so the current was earlier flowing when the transistor was on, the current was flowing like this from the battery to the transistor through the winding. And since the inductance is present here, if we switch off this, the diode will come into conduction. So, the current will free will like this. So, when the diode is on, we say that V is equal to minus VDC and the current decreases. So, when the transistor is on, V is equal to VDC. So, we can say I increases, I is this current, the current through the winding, I increases, and if T is off and the diode is on, V equal to minus VDC and I decreases. So, this is how it happens, and we can write down an equation for this. Say we have this inductance in this case. So, we can say that V is equal to VDC, let us say that is equal to Ri plus N d phi by dt, the flux in the winding. So, neglecting the resistance drop, because the resistance drop is quite small, it is a copper winding which has got a resistance also. So, we can say that VDC is equal to N d phi by dt. So, what is phi here? Phi is the flux, that is equal to VDC by N into dt, that is equal to integral of VDC, we divide by omega here and multiply by omega. So, if we multiply omega into dt, omega is the speed in this case. So, what we get here is integral of VDC by omega n, and this becomes d theta. So, we assume that the first condition is applied, this is the first, this is the second condition. For condition 1, so we have this equation. So, the flux is given by integral of VDC by omega n into d theta. So, if we integrate this, what we get here VDC by omega n into theta. So, we see that the flux in this case increases linearly with theta. So, the flux increases linearly with theta. Similarly, when we apply minus VDC, flux will decrease linearly with theta. So, this is the conclusion that we have here. And what about the current? The current is nothing but N phi by inductance. So, the current can be obtained as N VDC theta divided by omega n, n and n will be cancelled. So, it is VDC omega n by L here. So, this is VDC into theta by omega L. So, this is an equation which gives the current in the winding. So, we see that the current in the winding of a Swiss reluctance motor, the stator phase winding of a Swiss reluctance motor is proportional to theta, theta is the rotor angle, and is inversely proportional to the inductance is the value L here. And by properly controlling the applied voltage VDC, we can increase or decrease the current, and that will basically help us control the torque. So, we stop here for today's lecture. We will continue our discussion on Swiss reluctance motor in the next lecture.